Earlier in this chapter, we looked at alkane conformations and we introduced several types of steric strain. The first is torsional strain, where bonds are essentially overlapping with each other. If we have an eclipse conformation, we have maximum torsional strain. If we have a staggered conformation, we have minimal torsional strain. We also have van der Waals strain, or steric hindrance. And this is when groups are too close to each other, so that atoms are forced closer than their van der Waals radius. Now in this video, as we begin to talk about cycloalkane conformations, we're going to see a third type of steric strain, and this one is called angle strain. So we're going to see some examples within cycloalkanes where an atom is forced to have a bond angle that is not the desired bond angle according to sp3 hybridization, for example. So in this video, we are going to focus on small cycloalkanes, beginning with cyclopropane. So the first cycloalkane we will look at is cyclopropane, a three-membered ring. Now we know that 3 points determine a plane, and so cyclopropane doesn't have any options for conformations because these 3 carbons are going to be in the same plane, in the plane of the screen. So these carbons are all in the same plane, which means that these hydrogens are all going to be eclipsed on each other. So we have a significant amount of torsional strain. For example, if we were to write this on its side, so here is a carbon and another carbon, and then let's put our third ring carbon behind. Now, if we're focusing on this carbon, we're going to have a hydrogen up and a hydrogen down. This carbon, we have our hydrogen up and hydrogen down because we're looking at it at this ring on the side, so perpendicular to the screen. And what you should notice is that these bonds are eclipsed on each other, and these bonds are eclipsed on each other. If we were to look at this as a Newman projection, so let's say we are looking this way, this is our front carbon, which is connected to a hydrogen and the carbon of the ring. And then let's call this one our back carbon. And our back carbon is connected to a hydrogen, and the carbon of the ring. So these bonds are eclipsed on each other, giving cyclopropane significant torsional strain. But another thing that's important to consider is that in this molecule, each of these carbons is sp3 hybridized, which means it wants a bond angle of 109.5 degrees. But in this triangle, what we have is angles of only 60 degrees. So this gives us a significant amount of angle strain. Atoms are forced to have bond angles of 60 degrees when they want to have bond angles of 109.5. So a way that we can try to picture this is if we have a carbon and it is sp3 hybridized, then here is an sp3 orbital and an sp3 orbital, one going back, one coming forward. So I'm trying to represent the tetrahedral arrangement. Now with another carbon atom, then we would have an sp3 orbital, an sp3, an sp3 going back, and an sp3 coming forward. So to have an effective sigma bond, we want those sp3 hybridized orbitals to be overlapped end to end. But if we have two atoms overlapped like this, then a third atom with its sp3 orbitals, these aren't going to reach, right? We've got space here, so they can't overlap. If we have a good overlap, then we can't have these other atoms overlapping to give us a three-membered ring. So instead, what we can think about is that, well, maybe we'll draw the first one the same. Here is our first tetrahedral atom, And then our second one, instead of having this effective end-to-end overlap, it kind of has to overlap at an angle. So it'll be kind of a glancing overlap, forward and back. And then here, we're going to have kind of a glancing overlap as well. So we can try to think about this as, because of the limitations of the 60-degree bond angles, then the tetrahedral arrangement doesn't allow for significant end-to-end overlap, which makes these bonds kind of weak, and it makes the ring highly strained. The next molecule to consider is cyclobutane. Now, if this is flat, then we would have torsional strain, because all of these front hydrogens would be eclipsed on each other, and all of these back carbon-hydrogen bonds would be eclipsed on each other as well. In addition, there would be angle strain, because we are looking at bond angles of 90 degrees instead of the ideal 109.5. However, experimentally, it's been shown that cyclobutane is puckered. So we could imagine that these two carbons, for example, stay in the plane, but these two carbons kind of come forward. So by puckering, this actually leads to an increase in angle strain, because instead of being 90 degrees, it takes on an even smaller angle, but that must lead to a significant decrease in torsional strain. Right, so experimentally, it is known that cyclobutane is puckered, and so it must be willing to take on an increase in angle strain in order to significantly decrease the torsional strain. Next, let's consider cyclopentane, a 5-membered ring. And once again, we can think about this. If the ring was flat, then we would have significant torsional strain, because all of the front carbon-hydrogen bonds would be eclipsed on each other. All of the back carbon-hydrogen bonds would be eclipsed on each other as well. But if it was flat, there would be very, very little angle strain, because we are looking at a bond angle of 108 for a regular pentagon versus the ideal 109.5. But experimentally, it is known that cyclopentane is non-planar. So if we think of this kind of like an envelope, then imagine that we are folding down the flap of the envelope. So cyclopentane will take on a conformation, a shape that looks kind of like this. Now, some of these carbons are still in the same plane, and so there will still be some torsional strain, but because this one is out of the plane, that is going to relieve some of the torsional strain. So this is another example where the molecule will accept an increase in angle strain in order to relieve some torsional strain. Now finally, let's take a look at cyclohexane, a 6-membered ring. And if this was flat, then we would have a lot of torsional strain, because all of the front carbon-hydrogen bonds would be eclipsed and all of the back carbon-hydrogen bonds would be eclipsed. In addition, there would also be angle strain, because we are looking at bond angles of 120 degrees instead of the ideal 109.5. But experimentally, it's known that cyclohexane is not planar, and it can take on several different conformations. One example, if we try to imagine that we take this and fold it down, and this one, and we also kind of fold it down, then we get something that looks like this. So these are in front and these are kind of behind. And this is called a boat conformation. So it's not very obvious from that perspective, but if we were to look at it from here, so we look at it this way, we're going to take this whole thing and turn it a little bit, then what that gives us is this is in front and here is our other carbons, and then this is back behind. This is the carbon on the left. Here's the front and the right, so left, front, right, and then these are in the back. And now, hopefully you can see that it takes on a boat shape, especially if we add a little sail. So now we have our little sailboat. So the boat conformation, we have less angle strain, but there is still some torsional strain. So there's another conformation that we need to consider. So let's imagine that we take this part of the boat and we fold it down. So that gives us another conformation that looks kind of like this. Now this is in front, this is in front, this is in front of the plane. We can think about this carbon and this carbon as being in the plane of the screen, and then these carbons are back behind. And this one is called a chair conformation. So in the chair conformation, this is our headrest. We have somebody sitting here relaxing, drinking their margarita on the beach after going on the sailboat, enjoying themselves in the chair. So we have the headrest and we have a footrest. Now with a chair conformation, we have bond angles of 109.5 degrees, so there is no angle strain. In addition, if we were to look at this bond, for example, let's imagine that we are looking down this bond. So let's say this is our back carbon, and our back carbon, we have a hydrogen going straight up, we have a hydrogen over here, and then this is connected to the ring. And then if we think about our front carbon, so here is our front carbon, and we have a hydrogen straight down, a hydrogen up here, and then this is the carbon that's connected to the ring. So all of our bonds are staggered. And so a cyclohexane chair is the most stable conformation of cyclohexanes because there is no torsional strain and no angle strain. So we are going to spend a lot of time looking at chair conformations because of their importance.